Welcome everyone. Let's talk about a 10-minute introduction or recap to reinforcement learning. Okay, let's dive right into it. So in reinforcement learning, we have our agent, which will be performing certain actions on the environment. And in response to that action, the agent will receive a certain reward and the new state S prime. And then the agent will continue to learn. And what the agent needs to do is it needs to learn to act to maximize the expected rewards based on the observed samples of outcomes. Okay. So in the mathematical context of the reinforcement learning, we will assume a Markov decision process, which has a certain set of states where the agent can go, a certain set of actions that the agent can take, and we are given a stochastic transition function and a reward function. So when the agent is in a certain state S, takes an action A, it ends up in a state S prime and receives a certain reward. Now, in this context, we're looking for the policy pi S, and we just don't know what the transition function or the reward function are beforehand. All we can do is we can try, and we might get certain samples, and from those samples, we might be able to learn what T and R are, but those will be just our estimates. So there are two broad categories of reinforcement learning technique. One is the model-based way, which is just like we said, we will learn the model, T and the R, using some sampling, trying to build our estimates. But there's another very attractive technique as well, model-free way, in which we will learn the state action values and the values of the states directly themselves. So there's a model-free way and a model-based way. We'll study both the approaches. Let's start with the model-based way. In the model-based idea, we will be learning the approximate model based on our experiences. Once we have that model, we will simply solve for the values, assuming that the learned model is correct, even though we know it's an estimate. So the step one becomes that we simply count the outcomes. Of course, it's probabilistic. So one time we might, even for the same state action pair, we might be thrown into state S1. In another place, we might be thrown into state S2. So we try this thing, and based on that, we normalize it, how many times we ended up in one state, the other state. So we develop our estimate of T hat, which is T circumflex. This is a symbol that's often used to denote the estimate of a statistical variable here. And we will build that MDP model. And then after that, we will simply learn solve the learned MDP model like we have done before. So this is the simple model-based way. Here's one quick run of it. We will try this thing 4 different times. Maybe we are in this state. We try to go east. Maybe we did end up in this area, or maybe we end up somewhere else. So we will build our episodes. We will take the average of all of them to build the T circumflex, the T hat, and the R hat. Once we have it, we will simply solve it like solving any other MDP. So this is one way. But like I mentioned, there's a very attractive technique of model-free way as well. This is a key mechanism to learn the MDP settings. In this, we don't even try to learn the T and the R values. We just learn the Q and the V values directly. If you recall the Q function, the V function, Q is a state action function, and the V is the value function of each state. We just try to learn this. And within the model-free way, there is a very standard technique, very popular technique called Q learning, in which we learn the Q values using the exponential moving average approach. Let's look further into that. Before we understand that part, let's focus on let's recap what is the exponential moving average. Exponential moving average is a super simple technique in which when we're trying to estimate this particular variable, once we have the new variable presented to us, the new value presented to us, we simply update our estimate using this learning rate alpha to take a certain percentage of the previous value and then use the new sample provided to us to average. For example, let's suppose alpha is 0.1, then what this sentence is simply saying is that we take the 90% of our previous value, take the 10% of the new value, So the new sample is going to contribute something, but it's not going to dominate the value itself. The previous one, the previous estimate still plays a role. And over time, we can decrease the learning rate alpha here. So these values start to stabilize once we have improved our estimates quite a bit. So the exponential moving average is a very general concept. It can be used in many different contexts. We are using here in the context of reinforcement learning. Also, in MDPs in general, whether reinforcement learning or not, just a reminder that between Q values and V values, you can compute one from the other, but there's a slight difference. If you're given the Q values, those are the state action values, you can actually compute V values very directly. It's a trivial, you simply take the maximum of all the Q values, and that gives you the V value. From the V values, we can also compute the Q values, but it takes a little bit more computation. So for that reason, it is actually much more preferable that we forget about the V values, just focus on the Q values, because we can always compute the V values on demand from the Q values. So that's what we will be focusing on here. And here's the Q learning algorithm in its entirety. Let me walk through it here. So essentially what we would like to do here in this Q learning, generally speaking, is to use this Q value update function. But of course, in this case, we depend upon T and the R, which we don't have. So instead, what we will do is we'll compute the average as we go. So we will run one sample transition, and we will get one sample value, QSA. We will then use the exponential moving average to plug that value into our previous estimate and use that to update our state action function. Let's look at an algorithmic way. It's a little easier to understand. And the overall Q learning algorithm is super concise and very, very, very straightforward. Here we have Q learning. We will initialize all the state action values to 0, good enough estimate. And we will start with a learning rate of 0.5. And we will keep doing this thing in a loop while the learning ratio is still some threshold value here. So inside the iteration, we will choose the state and a certain action, and the environment will return us a new state and the reward. We will compute the value of the new state by taking the maximum over all the actions from the state action estimates that we have. And the value that we will receive from that will be, so this factor here essentially represents the sample value, R plus gamma V S prime. Gamma here is a discount rate. So using that, we update our state action function using the exponential moving average to 1 minus alpha, the previous value, plus alpha times the new value. And we will keep changing the alpha. We'll keep decreasing the alpha little by little. Now you can choose these values 0.5, 0.001, 0.8 to your advantage. But as long as you choose these values meaningfully, your Q learning will learn very well. And the amazing result is, this is popular result known from Watkins and Diane's work back in 1992. It was called Technical Note. And what this says is the Q learning converges to optimal policy, even though we don't quite know how we select the actions. And we'll talk about how to select the actions in a different video. But just a quick recap, reinforcement learning is a super simple technique. It's a good, easy technique. It's very intuitive. There are two different ways, the model-based way, the model-free way. And this is different from just learning MDP, which is an offline planning. And now you should be able to easily explain what reinforcement learning is to somebody who doesn't know it, including two different broad categories of reinforcement learning. In a follow-up video, we'll talk about how to choose the actions and when to take the actions that we know of, when to try new different actions here. That's all we have for today. Keep learning.